Let's take a look at the final review solution set for Chapter 6, which deals with a few different math concepts, including using properties of exponents, graphing polynomials, some special case factoring examples, and also the exponential growth formula. We can see here that the first problem deals with using properties of exponents. Now, we learned the properties of exponents on a very basic level, and now this is our chance to put those properties together and simplify more complicated expressions. The expression here is the value of 3x squared y all raised to the 5th power divided by 9 times x to the 10th times y to the 6th. Now, if we will remember some of our exponent properties, one of them is the product power, which says that if we have terms being multiplied in a set of parentheses together, such as the case in our numerator, then we can distribute the exponent to each term that's being multiplied in the parentheses. So as you can see here, when we have this entire value raised to the 5th power, our property tells us that that same value is 3 to the 5th power times x squared to the 5th power times y to the 5th power. We can then raise each of these terms to the 5th power. 3 to the 5th equals 243. X squared to the 5th power brings in another exponent property in which the exponent, when raised to another exponent, the relationship is multiplication. So in this case, the exponent 2 is being raised to the 5th power. That relationship is multiplication when you raise an exponent to another exponent, and that is where x to the 10th power comes from here. That same property is in play here. There is an invisible 1, so y is being raised to the 1st power, and so y to the 5th power is essentially 1 times 5, and that is where y to the 5th power in the numerator comes from over here. Now, the denominator does not have any exponent properties in it that we are going to use just yet, so we are just transferring that value over as we simplify the numerator. Once we do simplify the numerator and combine it with the denominator, we do have some other exponent properties that come into play. We can essentially combine like terms, and we can understand this large fraction as multiple fractions being multiplied together, where we can split them up based on like terms. So 243 over 9 times x to the 10th over x to the 10th times y to the 5th over y to the 6th. And we can see that if we just multiplied our fractions and multiplied straight across, numerator times numerator times numerator, and denominator times denominator times denominator, we would wind up with this expression over here. So we know that we haven't changed the value of the expression. But now we can see that some other exponent properties come into play. The quotient property of exponents. So we know that when the bases are the same, and we are in a quotient example or a division example, the numerator exponent minus the denominator exponent is the simplified version of that value. So x to the 10th over x to the 10th becomes x to the 10 minus 10 power, which is where x to the 0 power comes from here. Y to the 5th over y to the 6th becomes y to the 5 minus 6, and that is where y to the negative 1st power comes from over here. 27 is simply the result of 243 divided by 9, because 27 times 9 equals 243. Now, a few more exponent properties are in play to actually get us our resulting solution of 27 over y. The first is the zero power property. So anything to the power of 0 equals positive 1. So x to the 0 power here equals positive 1. And that's why it is not present in our final solution, because this is essentially 27 times 1 times y to the negative first. Also, we have our negative exponent property in play. And our negative exponent property, we will remember, says that when we have a base raised to a negative exponent, like y raised to the negative first power, a negative exponent does not have anything to do with a negative number or a negative value. It states that the value is the reciprocal of the base raised to the positive version of that exponent. In this case, we have y to the negative first, so that would become 1 over y, because y as a fraction is y over 1. The reciprocal is 1 over y raised to the positive power of 1. So y gets dropped to the denominator, to the positive 1 power. 27 stays in the numerator of our solution. And hence 27 over y is our simplified expression from our original, more complex expression up here. It incorporated basically all of the exponent properties. We are also taking a look at graphing polynomials. We have already shown graphing quadratic functions, graphing parabolas. But if we know our properties of exponents and we know our basic input-output relationship, then we have the ability to graph any polynomial in a function form. So we have the function f of x equals the opposite of x cubed plus 2. Graph this polynomial function. We are given an xy chart here, and in order to graph this polynomial function in a two-dimensional xy coordinate plane, we can create some ordered pairs, some input-output values, plot those ordered pairs, and then graph the function. So the work is shown here. When our input value is negative 2, notice this states that f of negative 2 equals the opposite of negative 2 cubed plus 2. Again, I stress using the parentheses when you are substituting values into a function. And I also stress the understanding that this negative sign in front of a variable means the opposite of whatever that value is. It does not have to be negative. So I would understand this to be the opposite of x cubed plus 2. And we can see here the opposite of x cubed. In this case, x is negative 2. Negative 2 cubed is negative 8. And the opposite of negative 8 is positive 8. So this becomes positive 8 plus 2, which results in positive 10 as our output value when our input value is negative 2, creating the ordered pair negative 2, comma 10. We take that same careful approach in terms of watching our signs and using parentheses and our order of operations, and the work is shown algebraically here to create the rest of these ordered pairs. Negative 1, comma 3, that work is shown here. 0, positive 2, 1, positive 1, and 2, negative 6 are the ordered pairs that are created. And again, the work is shown here to produce those ordered pairs. On the following page, those ordered pairs are simply graphed, and this is the resulting polynomial function. This polynomial function comes down here, curves through the point 0, 2, and then curves back down through the point 2, comma negative 6. We took a look at some special case factoring scenarios when dealing with polynomials, and one of those was the difference of cubes. So we looked at a few different models. If you'll remember, we looked at the difference of squares model, the sum of cubes model, and the difference of cubes model. Each of those is something that we want to understand in terms of what that model looks like and how to apply that model and how to recognize it. In this case, we have one of those examples, and that is the difference of cubes. So the difference of cubes models states that the value a cubed minus the value b cubed produces this factoring example and this factoring pattern, which is the value of a minus the value of b times the value of a squared plus a times b plus the value of b squared. Now, the idea for us is to certainly recognize what these base values are. So if we recognize that this is a difference of cubes example, or if it's a sum of cubes example, or a difference of squares example, one of the most important things is to recognize what these base values are. In this case, what is the actual value of a? What cubed produces 8x cubed? What cubed produces 125? And in this case, those two base values are 2x and 5. Because 2x, the whole thing cubed, produces 8x cubed, and 5 cubed produces 125. As we can see here, we are then simply following this pattern and inputting those values into our factoring pattern here. I will point out that when you are looking at a squared, it is not simply adding an exponent of 2 to the end of our a value, that it is the value of a squared. And as you can see here, the value of a is 2x. So notice the parentheses. It is 2x, the whole value, squared, which produces 4x squared. And the same is true for our b value. In this case, it is simply 5, and 5 squared is 25. But we want to be careful and understand what those base values are and how to apply them to this factoring pattern. The last math concept here is going to be an exponential growth model, which specifically calculates the compound interest and the resulting balance. So if we have an example such as this, we understand that the exponential growth model is one that states the final value, a, or the total, a, is equal to P, which stands for the principal amount or the initial amount, times 1 plus R, which is the interest rate, to the power of T, which stands for time. And that depends on what the compounding interest rate is going to be in terms of time. Is it going to be compounded yearly? Is it an annual interest rate? Is it a monthly interest rate? And so the problem will determine what value of T in terms of how much time passes in terms of how much interest is being calculated. Our example problem here states $250 is deposited in a bank account with a 9% interest rate compounded monthly. What is the account balance after 3 years? We of course want to understand what our variables are represented as. So $250 is deposited into the bank account. That is our P value. That is our initial amount. So we initially go to the bank and deposit $250. It says that the interest rate is 9%. When we are dealing with percentages, we are going to be dealing with them in their decimal form. So we want to understand how to convert from percent to decimal. And percent is always out of 100. So 9% is essentially 9 divided by 100, and that decimal value is 0.09. That's 9/100ths. We can understand this is our tenths place, and this is our hundredths place. So this is 9/100ths. Our t value, we have to remember, is being compounded monthly. So it's compounded monthly, and they want to know what the account balance will be after 3 years. So we have to understand months in terms of 3 years. So if it's compounded monthly, after 3 years, that means 36 months have gone by. It's been compounded 36 times. So our t value, our exponent here, is 36. We now have the values in order to create the value of our total amount after those 3 years. So A equals 250 times 1 plus 0.09 to the 36th power. Again, we are using our order of operations, PEMDAS. So we are simplifying our parentheses first. 1 plus 0.09, 1.09. Again, now we are going to exponents, parentheses, and then exponents. So we want to raise 1.09 to the 36th power first before we multiply by our principal amount. That is a common mistake. Please keep that in mind in terms of our order of operations. 1.09 to the 36th power yields a value of 22.25 when it's rounded to the nearest hundredth. And then 250 times 22.25 gives us our final amount of $5,562.50. That is the amount of money that will be available in the bank account after 3 years. After $250 is deposited initially, that bank account has a 9% interest rate, and that is compounded monthly. So after 3 years, there will be a total of $5,562.50 in that bank account with this criteria.